You ever look at a picture and just completely miss something that's hiding in plain sight? Well, today we're cracking open a research paper that tackles that exact problem, but for computers. We're going to turn some seriously advanced theory into a practical guide, a blueprint for using quantum-enhanced AI to teach a computer to see the unseeable. I mean, let's face it, computer vision is everywhere now. It's the magic that helps a smart car swerve around a pedestrian or lets a drone zip through a forest. It's a fundamental part of our modern tech world. And, most of the time, it works amazingly well. But that's the real question, isn't it? That's where it gets tricky. What do you do when an object is actively trying to blend in, to camouflage itself? I mean, this is tough for our own eyes, let alone for an AI. And that's exactly the puzzle we're going to solve today. How to spot something that's doing its very best to hide. All right, so let's officially kick things off. We are diving headfirst into the camouflage challenge. And at its heart, this is what's known as a classification problem. So before we get to all the wild quantum stuff, let's make sure we've got the basics down. Image classification is really simple at its core. It's just about teaching a computer model to look at a picture and slap a label on it, like wolf or background. Our job is to make our model insanely good at telling the difference, even when that wolf looks almost identical to the background. Now, for a problem this tough, your standard issue tools just aren't going to cut it. We need an upgrade. It's time to open up a brand new toolbox, one that's powered by the, frankly, mind-bending rules of quantum mechanics. And the first tool we're pulling out of this box is the qubit. Okay, think about a regular computer bit. It's like a light switch, right? It's either on or off, a 1 or a 0. But a qubit, it can be a 1, a 0, or, and here's where it gets weird, both at the exact same time. This one little difference gives quantum computers a massive exponential power boost. Yeah, this whole both at once idea has a name: superposition. It's the secret sauce. It's what lets a qubit check out a huge number of possibilities all at the same time. While your laptop has to check one path, then the next, a quantum computer can basically explore them all in one go. So how do we actually harness this power? We're going to use a method called quantum annealing. And the best way to wrap your head around it is with this analogy. Imagine your problem is a giant, rugged mountain range with tons of valleys. The single best solution is hiding in the absolute lowest, deepest valley. Well, quantum annealing is a process that lets the system just naturally settle into that lowest point, effectively finding the perfect answer for us. And just so you know, we're not talking about science fiction here. This is the actual hardware. You can see how a regular laptop connects right to the D-Wave system through the cloud. You send your problem over, it gets scheduled, and then it's run on the quantum processing unit, the QPU, which lives inside that huge, super-cooled cylinder. This is real. Okay, we have our challenge, we have our quantum tools, so now what? Let's put them together. And for all you coders and computer science students watching this next part is for you. This is the step-by-step blueprint for building our quantum vision system. The brain of our whole operation is a special kind of neural network called a restricted Boltzmann machine, or RBM. What you need to know is that it has an input layer, the visible units, and then another layer of hidden units that are really good at finding features. And here's the key. The connections only go between the layers, not inside them. That unique structure is what makes it perfect for running on a quantum annealer. And this diagram just shows it perfectly. See the visible nodes down at the bottom marked V and the hidden ones up top H? Notice how all the lines connect a V to an H, but there are 0 lines connecting a V to another V or an H to another H. That's the restricted part in action. It's a simple rule, but it's incredibly important. All right, here we go. The whole process in 6 steps. First, you ingest your images and their coordinates, and you convert all that into a big numerical matrix. Second, you split that data up, some for training the model, some for testing it later. Third, and this is the really cool part, you train the RBM using the quantum computer. Fourth, you export that newly trained model back to a classical machine. Fifth, you let it loose. You use the model to make predictions on your test images and plot the results. And finally, step 6, you check your work, see how accurate the predictions were compared to reality. Now there's one more tool we can add to really boost our accuracy, and it's called QBoost. It's a really clever trick that also runs on the quantum annealer. The big idea is you take a whole bunch of simple, weak models, classifiers that are barely better than a coin flip, and you combine them. By weaving them all together, QBoost creates one super-powered, strong classifier that's way more accurate than any of the little ones on their own. So we've got the theory, we have the tools, we've got the step-by-step plan. What happens when we actually hit go? Let's see how this whole blueprint actually performs out in the wild. And here it is, the payoff. On the left, that's our input image. You can see the wolf, sure, but it is blending almost perfectly into that rocky background. It's a tough one. And on the right, that's our output. Our hybrid quantum classical model drew a perfect bounding box right around the animal. It literally took the unseen and made it seen. This really drives home the main point. This is not about quantum computers replacing classical ones. Not at all. It's a hybrid approach. We use the quantum annealer for the really hard part, training the model, and we let the classical computer handle everything else. That teamwork gives us a seriously powerful solution for problems that used to be, well, almost unsolvable. Okay, this one example is fascinating for sure, but why does this matter to you right here, right now? Let's zoom out a little and look at the bigger picture of where all this is going. This technology is not standing still. I mean, just look at the raw growth in D-Wave's hardware. Back in 2017, they had a system with just over 2,000 working qubits. Fast forward to 2020, and that number jumped to over 5,500. And today, they're pushing past 7,000. This is exponential growth, which means the kinds of problems we can tackle are about to get a whole lot more complex. And this power is already being used to solve real-world business problems. I'm talking about things like drug discovery, designing new proteins. A grocery chain in Canada cut a delivery optimization problem from 25 hours down to 2 minutes. It's being used in finance, e-commerce, and even to optimize traffic lights across a whole city. This stuff is happening right now. The research paper we've been digging into this whole time ends with this really powerful thought. This isn't just an academic toy anymore. The people in charge, the CTOs, the CIOs, they're paying attention. The adoption of quantum computing isn't a question of if anymore, it's really just a question of when. Which brings us to our final question, and this one's for you. As these two massive worlds of computing, quantum and classical, continue to merge, they're going to give us tools with unbelievable power. We're going to see problems we once thought were impossible become solvable. So what's the first unsolvable problem you're going to tackle?